any type of data, noisy data, clean data, multi-fidelity data, multimodal data, and physical laws in our case will be Navier-Stokes equations. So here's what if you have not seen any pins before. Here's one pin. We have in this dotted line, the first dotted line with the x1, x2, the blue circles is the input, and then u1 and u2 will be the outputs. In this case, we solve a solid mechanics problem. We have displacements, let's say, sigma are the activation functions. And then we realize that, of course, to obtain U1 and U2, you need a lot of data. So and the math is very simple. You can see here down here the mean square error, MSE for U, is simply a mismatch between the data that you have, if you do lots of experiments, let's say 10,000 experiments, and what you predict for every pair of data. Pair of data, x1, x2, and u1 and u2 forms one pair of data. So you look at the mismatch of that, and you have set up an iterative process, and you minimize the mean square error. In that process, you find the connections of the neural network. However, we don't have 10,000 experiments. We have probably 2 or 3 experiments or no experiments at all. So in that case, we know that u1 and u2 are differentiable functions, and therefore we can take derivatives, first derivatives, second derivatives, and so on. And then if we can do that, and I do that using automatic differentiation without any grid, I don't have to build a grid or a mesh, which is very tedious and very time consuming, just to have a grid for the solution and the operators. But here the operators are obtained using automatic differentiation, using computational graphs. So having now these operators, then you can try to satisfy these equations, namely F1 and F2 are the residuals. We have to make this 0, sigma are the stresses here. So now down in the bottom of this slide, we have what we call the physics, namely the minimization of the residuals, F1 and F2. F here is a vector. So then we can put them together. We can take a linear combination of the first term on the left, the data, and the second term of the right. So now we take the data, whatever experiments you have. If you have no experiments, no experimental data, this term is 0. Then we have to rely on the second term, just like we do in CFD today. But notice that we can have some data, a few data points, and then we can combine them by using a linear combination of the physics and the data. When we formulate this final or the total mean square error, which is called the loss function, then we use one of the standard optimizers to minimize the mean square error, to find the minimum of the loss function. Now the question is, where do you evaluate, at which point you evaluate this conservation loss, the Navier-Stokes equation in our case? And here on the left, I have a sketch that shows the domain, XY domain. The green point is where I have the boundary data. And then the purple points are where I compute the residuals of my conservation loss. And you can see these points are random. In other words, we use this method using Monte Carlo sampling in space and time. So that's what makes it powerful, because we don't have to build grids. So anybody can implement it. So I'm going to give you an example of the Berger's equation. Of course, Berger's equation is a simple model for turbulence. So ut plus ux, there's a nonlinearity, it has a second derivative in x equals 0. So the data here, I don't have any extra data. The only data I have is at t equals 0, this vertical line, this crosses, which is the initial condition. And then I have the boundary conditions here with the black points. Notice that even this simple equation that we teach our graduate students, first-year graduate students, cannot be solved with conventional methods, because if you look at time t equals 0.4, around there's a big gap. So there's big gaps in boundary conditions. So during these periods, we don't know the boundary conditions, therefore this problem is not well posed. Here, that's not the issue at all, because we are solving an optimization. We are formulating this problem as an optimization problem. So I also have some code in TensorFlow. We first define the neural network. The neural network is U, is the unknown function U. We already said that the neural networks approximate functions. And then we define the residual of this equation. We take the time derivative, we take first derivative, second derivative again, and then we add the terms up, and we have f, and then down here, we need to evaluate this term, this um, residual at random points. Random points, this is x is vertical, t is horizontal. So random points, we sample Monte Carlo random points here, and then we have the first term, and we take the loss function. So this takes about, you can see the code is very short. It's 10 lines of code. So everything is simplified because we don't have grids. All the derivatives are done using automatic differentiation, using computational graphs. Then 10 minutes later, with a very simple implementation, we get pretty good solutions, much better without overshoots and undershoots, although we have shocks here. So this shows the potential of this method in solving problems in fluid mechanics, low speed and high speed. This is what happened, what we published in 2017, and I wanted to give you an update of what happens to pins more recently for the same equation. So here on the left panel, I have the relative error, L2 error. There's a number of iterations. You can see we're converging. But in 2017, the error was this green curve. Now, with a new method of tackling the optimization problem, namely this self-scale Broydens method, we can actually get to this orange curve, and it shows huge improvement in accuracy. In other words, between 2017 and today, we have improved the order of accuracy by at least 3 orders of magnitude. This is for a Bergius equation, but I have it also for other problems. For example, the Kuramoto-Zivazisky equation used sometimes in combustion and dynamical systems. You can see some pictures here. We couldn't actually solve with pins at that time because we didn't have the right optimizer. We have first-order optimizers, and second-order optimizers were not very good. But now with these self-scale optimizers, we can get accuracy 10 to the minus 5, which is very respectable. And Gauss-Landau equations for perturbation analysis and so on. So pins have been very successful across many domains. Here I asked ChatGPT and DALI to make a summary of applications of last year. And you can see from geophysics to climate to biophysics, finance, heat transfer, and fluid mechanics, of course, there's many, many papers. And in fact, there's this library called DeepXDE, which we made public in 2019 and already has 1 million downloads from around the world. So let me concentrate now on answering the questions about hidden fluid mechanics that I posed earlier. So here I use the velocity pressure formulation. I have now a system of equations and boundary conditions. So notice that I have several residuals, E1, E2, E3, E4. All my residuals for every equation have one residual, so I will form one term in the loss function. And then I have to also have initial conditions and boundary conditions, and then I take a linear combination of all my losses from the governing equations and initial and boundary conditions. So taken together, then we have the loss function. When we get the loss functions, we just use one of the minimizer. I just talked about a good minimizer, which is a second order minimizer. So let me go back to the flow past the cylinder. It's something that I actually started back in my PhD thesis at MIT. And you can see here, it's on the cover of the Department of Mechanical Engineering in Massachusetts Institute of Technology, 1984, 1985, when I first did this simulation. And as I develop new methods, I always go back to this method. It's sort of my first project, serious project, and landed me on the cover. So here, I asked my postdoc to consider the following. Imagine you have some flow visualization downstream in an arbitrary domain. Can you obtain from that visualization the velocity and the pressure field? Okay, so clearly it's an ill-posed problem. We don't know anything about the object upstream, which is a circular cylinder here. We only know what we see in the video. So I have a video of a flow visualization. So as I said, this is a flow that I have studied a lot. 10 years later, after this, I have another cover. And another 10 years later, we have another cover when we were looking at the physics review letters, when we were looking at noise inflows. And now we are studying it again. And so this work was published again in Science. So what we have, in addition to the governing equations for the U and the V velocity and the mass conservation, we also have this first equation, I don't know if you can see on the right here on the top, says E1 is basically the conservation of, it's a passive scalar equation, that vector diffusion for the scalar. And we don't know the Peclet number, but we assume we have a video of the dye visualization. Okay, so we have that in time. And so if we have that, then we can actually use it in the loss function as data, and then we can get the weights and the biases of this pin network. If we get the weights and the bias, we simply sample them to find U and V, because this is one big network. It's not a separate network for each variable in coupled problems. So here in the colorful plots, what you see is the learned velocities, for example, on this row, and then from CFD simulations, we can see that we get the right, there's one very good agreement. Now, the question was that I posed was, can you also obtain the forces? In order to obtain the forces, the dye has to go around the body. In that case, the answer is yes. In fact, here you can see that we imitate the what was one of the reviewers asked us to look at the album of motion by Milton Van Dyke from Stanford University. And we obtain strict lines, as you can see. And then from strict lines, again, these are strict lines will be data that go into the loss function. And you can see that we can compute the lift coefficient, the drag coefficient within less than 5% error. And again, we don't know the Reynolds number in this case. We don't know the Peclet number. Of course, we use here CFD data to obtain this instead of real data. The same thing can be used the same ideas can be used. We can use pins to find closed turbulence models. For example, here we write the Rance equations without modeling, without the Prandtl modeling of the Reynolds stresses. So Fx and Fy are unknowns. So then what we want to do is from the mean field, U, V, and P, which are the resolved quantities, we want to obtain the stresses. We can use a pin, and here I show that if you ask this problem using DNS data for a K omega model, state-of-the-art turbulence models, the errors are 150% for the V prime, you can see here. So OpenFOAM and all the commercial codes out there gives huge errors for this problem. So the idea here is to learn directly from the data if you have some measurements. And the measurements here, in this particular case, I take a subdomain, and the only data I have is UV and the Reynolds stresses, UV Reynolds stresses, on the boundaries only. And the Reynolds number is here 3900, the flow is already turbulent. So you can see on this red line of this box, I don't know I don't have any information inside. However, using pins with the equations that I show you, the Rance equation without the closure model, we can actually obtain the Fx and the Fy, and we have reference data from DNS, and we can get errors which are 5 times smaller than the state of the art. We can actually do better if we have data inside. As you can see here, these are still synthetic data, but the errors go down to about 5%. Now I can use real experiments, and these are experiments from the University of Central Florida at Reynolds number 11,000. It's an ongoing project we have with DARPA. And you can see in all cases, we have errors which are less than 5%. So these pins also can be used for closure modeling. I go to the biomedicine now, biofluids. So again, this is on the right, you see the picture that the neurosurgeon would see. It's a black and white video of the contrasting agent, the tracer. So what we do is we have to write an equation corresponding to what we see. And here we write for the intensity, we consider that as a passive scalar that represents the passive scalar. So we write an advection equation. We omit diffusion here. For the flow field, the model for the flow field is a non-Newtonian fluid because we want to account for nonlinear effects. So again, the information that we have will go into the first equation, and then we'll pass that after we find the weights and the bias, we distribute them to the velocity and the pressure. That's how we find the velocity. So if we do that, then we can infer in 3D inside this aneurysm, 3D aneurysm, we can infer the physics, we can infer the concentration, of course, we match the concentration, and then from that we infer the velocity and the pressure in 3D, and that if we have the pressure, we get the forces due to the pressure. If we have the velocity, we take the derivatives, we get the wall shear stress, and from there we can actually obtain the yield stress, and then we know precisely when this aneurysm will rupture. So we pass that information to the clinicians. I want to also show something that we have it's still unpublished, something that we use data in a live mouse, and that is what is the flow field inside the brain. And I'm not talking about the blood through the arteries and the arterioles, but actually the cerebrospinal fluid, CSF fluid, which is like water that goes through all the porous regions of the brain. You can see that the CSF is produced deep in the brain, and then it goes into a perivascular space. In earlier work, we actually published a paper in Proceedings of National Academy of Science where we were able, using particle tracking, like I talked about before, to obtain the velocity in the perivascular space. But nobody ever has been able to infer or measure the pressure and the velocity field deep in the brain. And this, we're talking about animal studies, not. So here's a comprehensive, maybe complicated view of this neural network, but you can see what happens. We inject a tracer into the brain of a live mouse. It's an anesthetized mouse. And then we follow using MRI, a deep contrast enhanced MRI. The magnet is about 9 Tesla. So we obtain the diffusion. We see the diffusion of the tracer through the brain, the entire brain of the mouse. What you see here in this blue slices are the midplane of the mouse brain. And you can see that there's all these white regions, is regions where they're impermeable. The fluid doesn't go there. So we want to obtain both the velocities, but also we want to obtain the permeability field, and we treat the physics here will come from Darcy's law. So we assume here that this is a porous medium, the brain is a porous medium. So we want to obtain the permeability, the 3D velocity, and the pressure are shown to the right, that these are the infer fields. I'm not going to talk about the details of how we train this, a little tedious. These are real data, noisy data. But you can see the first thing is, again, in hidden fluid mechanics, you try to use the concentration field, and from the concentration field, to match the concentration field, and you can see the velocity field appears in this equation. Therefore, we are able, if we invert this, which is a very difficult problem in 3D and complex geometry, we will obtain the velocity field. And indeed, we did that. And here you can see, I don't know if you can see a movie, it's a 3D reconstruction of the velocity field. Red here means high velocity, high here means 10 microns per second, and then blue means 0, and then yellow will be something like 3 to 5 microns per second. So this way, for the first time ever, we have identified all the regions of the brain where CSF goes, and we not just in a qualitative form, but also in quantitative form. In particular, here we have the various regions of the brain where we see, for example, to the right, which is this red spots, that's where the circle of Willis. Humans also have a circle of Willis. And we have 5 different mice. Here on the top, I have the equations. You can see that how we get the pressure, and then we can get the velocity. We can get from Poisson equation for the pressure, we can get the pressure also. Then if I go back to my other problem, flow over an espresso cup, this was also something that we published in General Fluid Mechanics and in Nature Physics Reviews. The idea again is to match the density gradient. That's what we get with the Sliden photography. Then we match the temperature, and then we match the pressure, and then we infer the pressure, and we find the velocity field, as you can see here. The details is the General Fluid Mechanics. So again, the same thing. From concentration, we go to the velocity field. The last example is this experiment that I talked about, particle tracking velocimetry for a turbulent jet from Division. The state of the art is shade the box. And you can see that basically with LaVision is able to get these visualizations in 3D. The Reynolds number of the jet is about 5,000. But as I said, they use a lot, 10,000 to about 20,000 vectors per snapshot and 200 snapshots in a very short time interval. So we want to do better. We want to downsample in space and time, in fact. And here's some more details. And these are our results. You can see that when we use, of course, 16,000 vectors like they do, we capture all the details, the potential core of the jet, and the turbulence breakdown. But even if I go to all the way to 64 times less than only 250 particles, I still get the full details of the rib connections through the vorticity and so on. Even for 128 times, only 125 vectors instead of 16,000 vectors, using the equations provide, so I have very, very sparse data, I can still visualize. In fact, as you can see here, the visualization is looks like DNS, but these are experimental data, reconstructed fields using pins. So that's about what I wanted to talk about pins. I hope you get this idea of how you can use pins in a creative ways, not just to replace your finite element or your spectral or finite difference method or finite volume. But what is the problem? The problem with all these neural networks are expensive. You may have heard that it takes about 20 megawatts of power for ChatGPT-5. And here I show how all this pollute the environment. For example, even ChatGPT-2 pollutes the environment has a much bigger effect than standard travel by plane and so on. So we want to do better. We want to come up with, instead of every time you change something in the model and you have to retrain, we want to come with a higher level of abstraction. And this led me in 2019 to introduce something called neural operators. And neural operators is a high level of abstraction. It's closer to human neurons instead of artificial neurons. So if we examine a human neuron here, we see on the left all these branches, which are called dendrites or branches. Then we have the soma of the trunk, where all the calculations are done. And then we have the axon where the information is passed to the connection here, the synaptic output. And then this is connected to another neuron and so on for downstream tasks. So the point, there are two main components here. One is the input, which is the branches, and another one is the soma or the trunk. So based on that, we construct a neural network that has two neural networks. And one is the branch, so what the input is, and here is the where the computation is done. Now, what's the difference between a neural network and a neural operator? Where a neural network, the input is data in, and the output is data out. And of course, the function that connects, what connects the two is a function. Here, we want the inputs to be functions and the output to be functions, solutions. Why we want the inputs to be functions? You can imagine a case where we don't want to retrain the network because we have different boundary conditions. Instead, we replace the static boundary condition with a boundary condition which is a function of space or time. So depending on what the specific flow setup is, we use this distribution. And then we pre-train everything offline, and then the neural operator works on online. Let me explain this again using a little math. What we have been doing so far is we map the input, RD1, in finite dimensional space, to a finite dimensional output space, RD2. For example, in MNIST, image classification, when we try to recognize the number 5, the handwritten number 5, that's what we do. All commercial machine learning does that. What we propose to do is a higher level of abstraction where the inputs are functions or distributions, if you like, and the outputs are functions, which are solutions. But the point is I deal now with functions, which can give me many different instances of the system I'm studying, and the different boundary conditions, and the different Reynolds numbers, and so on. So this way, I don't have to, every time I change the Reynolds number, every time I change um, the inflow conditions. I don't have to, or the viscosity, I don't have to train again and again, therefore making huge savings of, it's just like ChatGPT. ChatGPT is a pre-train and then works in real time. Um, it does inferences in real time. So we want to produce something like that, but here for fluid mechanics. So first of all, we have to prove that these operators exist. So in the paper we published in Nature Machine Intelligence, we actually show that g of u of y, which is the operator g, so we take u as an input and we map it to g of u of y, can actually be uh, approximated with two networks, the branch and the trunk. So these are deep neural networks because the original theorem was for shallow networks which don't work in real applications. So we proved that. And so I want to show you now how this works in one example and then a couple of examples, but I'm almost done. So let's look at this bubble dynamics. This equation here is called the Rayleigh-Plesset equation. It goes back to Lord Rayleigh, which connects the pressure between the center of the bubble to the ambient on the left-hand side and the radius of the bubble. Of course, we know how to solve this equation using, let's say, finite difference methods in MATLAB. But here we pretend we don't know the equation. We just use this equation to produce data. Then using the data only, in this case, not the physics, not the equations, using the data only, we'll try to find the operator. In this case, the operator is really this whole equation. Okay, so we solve an inverse problem where they give us data and we try from the data directly to infer the radius as a function of time. So the data here will be the pressure difference. So you give me the initial radius size, you give me the pressure difference, I have to infer the radius as a function of time without solving this equation because I don't know this equation. In fact, I will try to discover these equations from data. So this if you can think of this operator learning as a system identification. So here on the bottom, I describe what I do. I have the pressure difference that goes into the branch. That is a function. It's a function of time here. It goes into a branch. And then in the trunk, we have the time. And then on the output, which is this when we cross the two together, it's a pointwise multiplication of the two, we get R. Okay, so here's on the upper panel here, on the upper right panel, you can see three arbitrary distributions of which we have not used in the training of this offline training of this neural operator. And then in the bottom, we have three corresponding predictions of the radius. You can see this is a multi-rate problem because we use, in the beginning, you can see very fast oscillations, and then the viscosity takes over, and we have a radius that changes slowly. So you have basically two frequencies, a high frequency and a low frequency. So typically, other networks like LSTM will do a good job if you use lots of points, 200 points per trajectory. But here on the compared with LSTM, which is a very classical method of forecasting time series. But you can see when I use only 20 points per trajectory, the LSTM fails to get the high frequency right. With DeepONet, you can see that we can obtain also the high frequency and the low frequency, and therefore we can use it now to obtain all type of forecasting the series. In fact, we can do it with on the left here on the vertical axis, you can see the bubbles, the initial size of the bubble goes from nanobubbles to millibubbles, milli-sized bubbles. But of course, below 1 micron, we cannot use the Rayleigh-Plesset equation because the continuum is not valid. Therefore, I have to use particle methods like the particle dynamics and molecular dynamics. So we published this paper in Journal Fluid Mechanics where we show that you can learn also the growth of nanobubbles, including thermal fluctuations. Okay, so I'll skip the details, but in this paper by Lin et al. In 2021 in Journal Fluid Mechanics, we have now a multi-scale operator because above 1 micron, these are all in microns, We have the continuum equation we discover. Below that, we do nanobubbles, and nanobubbles are very, very difficult to simulate. One nanobubble simulation takes about 50 hours on a parallel computer. Here, because we don't train the operator knows how to grow bubbles. It takes very fast. The same thing can be used in compressible Navier-Stokes equations here. Um, and we've done that for hypersonics. And so basically, from signals, let's say from flow over a boundary layer, and you can see here a transition from these pressure transducers from laminar to turbulence, you can use these signatures to invert the problem to see if there is any disturbance in the inflow. Then you determine the inflow and you solve the forward DPONet, and you can really simulate transition. This is something that we published in collaboration with people from Johns Hopkins a couple of years ago. You can solve difficult problems like Riemann problems for high speed aerodynamics, where the pressure from the left side and the right side is very large, and you get pretty good accuracy. And the reason we get pretty good accuracy is because the trunk produces a basis which is very similar to the real problem. So we can pre-train the trunk. You can see here the mode 0, basically the first eigenfunction from the trunk, and then the 10th eigenfunction. You see it has oscillations, has all these discontinuities. Even the last mode that we will capture in this adaptive basis I talked about earlier, you can see you have like a Fourier series, and then you have a constant state, and you have like a wavelet. So it gives the basis, the adaptive basis, as I said earlier, in the best form. So this is my last slide to show that DPONet provides a plurality of neural operators. Since we introduced this concept of neural operators, there have been a lot of neural operators, Fourier neural operator, and Caltech, and we published neural operators and so on. Most importantly, the branch doesn't have to be a fully connected neural network. It could be a graph neural network or a spiking neural network, which is even more by closer to human neurons. Then similarly, for the trunk, we can have different neural networks. So one can plug and play. Therefore, we have a plurality of neural operators corresponding to different architectures. So a DPONet is a sort of an abstract framework. One can build different representations. If you're interested in learning more about it, I have developed a course for NVIDIA. You can see here the website. It's a free course. It's 40 hours of video. And you can see here we teach all the frameworks from TensorFlow that I talked about to PyTorch and JAX. And now we also will include in the future MATLAB, because we work with MathWorks to implement MATLAB for machine learning. And then in module 2, we have pins and operators I talked about here briefly. And then in module 3, we have advanced topics. We talk about the modules library from NVIDIA, which is now called Physics NeMo, multi-GPU scientific machine learning, and also various projects. So with that, I would like to thank also my sponsors from the Air Force and my collaborators from various universities, and also this Department of Energy center that I direct from Northwest in the United States, in close to Seattle. So thank you very much for your attention. I'll be happy to answer questions. I can barely hear you. Maybe closer to the mic, or maybe where the laptop is. Yes, now it's very clear. Thank you. Yeah. Yes, the answer is yes. You have to enhance pins with um, an extrapolation capability. So there is some people at Stanford and Holland wrote a paper. They called it neural oscillator, where they combine pins with um, an LSTM, for example, or a neural ODE, and uh, uh, that addresses exactly this issue of long time integration. So from short trajectories, you learn um, in the neural network, and then you use an LSTM. There are other networks also you can combine, which is forecasting time, and so you can do that. So it is possible to do that, and if you can look up the paper by Daniel Tartakovsky on the neural oscillator, does exactly that. They have examples like that, exactly like what you described with the Lagrangian particles. But for example, in the PTV, in the experiment with the turbulent jet, that's what I was doing, right? I was tracking particles in a Lagrangian fashion. So that can be incorporated, but what you're asking is can you extrapolate? And in order to extrapolate, you have to add a LSTM or an other recurrent neural network to the pin for more accurate extrapolation. Did I answer your question? Okay. Right. So that's the question that everybody asks me all the time. So pins, pins in particular, um, as I demonstrated, can be used without data or with data. When you use, uh, if you have, if you have no data, then we're talking about CFD. So pins look like CFD. Now there are, I work in CFD before I got into this. And the problem I have with CFD is that if they give you some data, then it's very difficult to incorporate the data into CFD. You have to use a join method. You have to use very elaborate data assimilation methods. And data assimilation is not really popular in fluid mechanics because uh, we sort of indirectly try to calibrate our models. So the answer to your question is yes. However, pins have been around only for a few years. These methods have been around for 100 years. Finite elements have been around for 70 years. And in the beginning, finite elements had lots of problems. The same way, pins are continuously improved. I show you today that pins have been improved in terms of accuracy, by 3 orders of magnitude since the original paper, just by changing the optimizer. So I believe sooner or later, pins will replace totally all the existing solvers, the classical solvers, because they're simpler. For example, a CFD code, my CFD code is 500,000 lines. Nectar, that spectral elements, is 500,000 lines. My Navier-Stokes solvers using pins is 500 lines. So it's 1,000 times shorter code. So if you ask your students, I think your students would like to write 500 lines of code instead of 500,000 lines of code. So the popularity will gain popularity more and more. But of course, there are some still issues that have to be resolved. Uh, just like we learn how to do CFD for turbulence, for DNS, we need high order methods, right? Low order methods would not be. So same thing with pins. We need high fidelity versions to deal with turbulent flows, for example. But otherwise, you can run them as CFD. So the answer to your question is yes, they haven't done it yet. For inverse problems, pins have replaced most all methods. But for forward problems, I think there's an issues that need to be resolved first before pins take over methods like my first book was on the spectral element method. That's a very accurate method, combines spectral methods and finite elements. That was my PhD thesis at MIT. That method is used now everywhere. At the time when I developed it, nobody wanted to use it. Now the biggest climate model in the world called E3SM uses spectral element method. But when I use when I developed in 84, 85, nobody wants to use it. So it takes time for people to get used to it. Here, in this case, because the method is very simple, people have started using it. So that's why I said there's 1 million downloads of the free library already. I hope that I answer your question. Yes. Okay, that was the surprising result. And you can see the details in the JFM paper that we actually use the same network to and feed it and fed it with data, this noisy data. In the JFM paper, we only look at the mean, so we ignore the stochastic fluctuations. But in the subsequent paper in the multi-phase flow journal this year, we also consider the stochastic fluctuations. But in the original paper, where we look at the mean radius, we use a standard. We use the same network for both, and we simply overlap the data around 1 micron, where is the demarcation line between continuum and non-continuum. So it worked really well without any handshaking, without anything extra at the at the boundary between continuum and non-continuum. But as I said, if you are to consider also the stochastic fluctuations, then you have to do something that is thermodynamically consistent. And in that case, we change the network to something else to also give us the fluctuations. Yes. Well, I mean, are you asking about neural networks in general or pins in particular? Yeah, in general, this neural networks are used a lot. Actually, graph neural networks. DeepMind has done some work, but this week, actually last week, one of my former students, Paris Perdikaris, who is now professor at University of Pennsylvania, published a paper on exactly that. It's called Aurora, and he produced a foundational model based on neural networks. And this foundational model was trained using all the data of all the hurricanes of all years, all the historical data there. And that Aurora now can forecast hurricanes or any other extreme heat waves, precipitation, monsoons in Southeast Asia, and so on. So indeed, that's a very good use of neural networks. Pins in particular can be used if in some components that you know the physics. But there's also the physics aerosol clouds and so on. We don't have fully knowledge of the governing equations for that. So you can use part of it could be pins, part of it could be just standard neural networks. But with some offline training, just like these neural operators I talked about. So you can look up the paper. I think that's the state of the art. And what they did was they were able to forecast um, weather events 12 days in advance, which is the record. I think 7 days. DeepMind can go up to 7 to 8 days, but they were able to forecast accurately the weather 12 days in advance. It's hard to believe, but that's what they published. Thank you. Muchas gracias.